Hello everyone. Hello everyone. So sorry for some interruption. So thank you so much for joining. Today we are talking about Markov models, that is processes, chain, a property or hidden Markov model. Then we will see some of the MATLAB simulations, then application, and finally some advantages and limitations, and then some conclusion. So as of all of you, we know that what is Markov process? A Markov process is a simple stochastic process in which the distribution of future states depends only on the present state and not on how it arrived in the present state. Okay, so suppose you have x of t, it's a present state, and it only depends on, so I do. So it is only dependent on x of t, it is only dependent on x of t minus 1, not subsequent t minus 1, t minus 2, t minus 3, t minus 4, like that. So if we say how states are related. So a finite state representation, if we can see, suppose there are some states H, E, T, I, A, P. So you can see the probability of going from state H to E is 1, whereas the probability of going from state H to T is 0.4. So how can you write like this? So you can write P of T by H is equals to 0.4. Similarly, you can write for other states. So this is a simple marker models like you can represent. Okay. So moving ahead, many systems in real world have the property that in given state, the past states have no influence on the future. And this property is called Markov property. I hope you all agree. Now, suppose you have time space like discrete or continuous, and state space as also discrete as continuous. When you have time space as discrete and state space also discrete in the sense you can represent in terms of number of steps, then it is a Markov chain. Okay, if the time step and state space are not discrete, so that is not a Markov chain. Now let us represent it mathematically. Suppose let xt, where t is in T, capital T, be a stochastic process. So from the previous classes, we know that what is a stochastic process with a discrete state space S and a discrete time space T. Satisfying this property, like if xn plus 1 is equals to j, given that xn is equals to I, xn minus 1 is equals to I minus 1, n minus 1. So it is equals to xn plus 1 j given xn equals to I. So what we are not considering these samples, previous samples. So it is nothing but what xn plus 1 is equals to j given xn is equals to I, xn minus 1 equals to I n minus 1, x0 is equals to I0. So what we are saying, these are the given states, but what it is equals to xn plus 1 equals to j, given only xn equals to I. So similarly, like we previously had, So now coming to the hidden marker models. In an hidden marker model, we don't know the state sequence itself. Okay. However, we know some probabilistic function of it. So in plain English, if the marker model can be viewed as a probabilistic finite state engine, the state is changing over time, but we have no way to determine the exact changes of the state. Now we are able to observe some fuzzy relationships or fuzzy reflections of the change. So our objective is to estimate the states of the machine via possible fuzzy observations. So there are some fuzzy observations, okay, but actually there is no there is no actual state space. Like previously, we had that space, state space. State space in the sense is you have this number of states, you have this number of uh, probability. Like you can go from one state to other state. But if you don't have that, okay, so that can be a probabilistic finite state engine, okay, where state is not fixed. It is changing over time. But we have also no way to determine the exact changes of the state. So now we have some observation and trying to have some reflections of the change. So state is changing or evolving over time. Okay, so we'll see some more detail on it. For example, the weather in Dallas of past 26 days. Dallas is one city. So we can say states equals to pretty, 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 pretty. Then you will have rainy, rainy, rainy. Then again pretty, pretty, pretty. Okay. So it's again changing. But there will be some relationship, like how it is changing. So that observation we need to find it out. Suppose today's weather is and tomorrow's weather. So you'll have today's weather is pretty pretty, tomorrow's weather again pretty raining. So what is the probability of rain from pretty to pretty? And what is the probability of raining to pretty? And what is the probability for this one? So these are the probabilities. Now we'll see some of the more example. Okay, so you have these things. So with if you are in the states rainy, so what is the probability of getting rainy only? There is only 0.8. Whereas if you are in state pretty, what is the probability of remaining in pretty? It's 0.95. So if what is the probability from rainy to pretty is 0.2, like that. Previously we can make, okay. So transition probability is this one. You can have pretty here, rainy here, pretty here, rainy here. Right. So yeah, Markov model example, hidden model. Many times we don't have a direct observation of the change of states. Therefore, we say that the model is hidden. Okay. However, we are still able to find some observation or emission of the state changes, and the emission could be fuzzy. Okay. For example, you are isolated in a closed room during an experiment, and in the room you have no direct observation of how the weather changes. Every day, one assistant is coming, delivers the meals for you once a day. The only way you can have a clue is to observe how the guy's dress changes. Then that is a hidden one. So actually, you can't see directly outside, but you are seeing that the guy which is coming to deliver the food, and from that you will have some observation. Okay. So Markov model example. In the room, you might observe that your assistant dresses with regular coat, a raincoat, or a brings an umbrella. So your observation can be regular code or umbrella, then regular code, regular code. There will be sequence of observations. Okay, that sequence we need to observe. Then uh, again we can have this observation like to the sequence. So pretty rainy, then regular code, raincoat or umbrella. So from if it is pretty, then most probably you'll have 5/6. If it is pretty, then you can have raincoat as 1/12. And these are the probability what you will wear. So this is not a transition probability. This is something different. It's the emission probability. Wait a second, it's not moving. I have to go like this. So sorry. Yeah. So mathematical elements, if you say, a set of states over time denoted by states, a set of emissions or observations over time denoted by sequence. Okay. SEQ. Now, an m by m transition probability. Okay. M by M transition probability whose entry is Ij is a probability of a transition from state I to state J. I hope that you agree, okay? But N by M by N emission whose Ik entry is the probability of emitting symbol Sk given this model is in state I. Please try to observe this, like what I'm trying to say here. So this is a like N M by N emission matrix, okay, whose IK entries gives that probability of emitting the symbol SK, okay, given the model in state I, that is correct. That is correct. I hope you all understood. Now let's see some observation or outlines. Markup models. Wait, what happened? Okay. Now we will see some MATLAB simulations. So why MATLAB actually? The MATLAB is a tool for doing numerical computation with matrices and vectors, and it can also display information graphically. So combined with numerous multiple mathematical libraries, MATLAB has become one of the few tools that can catch up with any ideas. So that's why MATLAB is being used here. So MATLAB compiler translates a MATLAB code to ANSI standard C code. With a MATLAB compiler, we will be able to automatically generate optimized C or C++. So you can see why MATLAB is used. Hmm? So if you have these functions like MCC, this will lead some direct direct translation of a MATLAB code to C++ code, and the compiler can significantly speed up MATLAB applications and development. So this MCC, okay, MATLAB compiler, MCC minus T minus L, C my function will yield my function dot C, okay, where MCC minus C minus L, C my function yields my function dot C. Okay, that is very correct. That is very good. Okay. So if you want to run main over this my function one, so this third command is for that. Okay. So MATLAB statistics also we have. These are hidden Markov model decode, then hidden Markov model generate, hidden Markov model estimate, hidden Markov model train, hidden Markov model Viterbi. So MATLAB runs demo.m in MATLAB 6.5 environment. Wait. Okay. So applications of Markov models are speech recognition, modeling of coding, non-coding regions in DNA, protein binding, sites in DNA, protein folding, protein superfamilies. So these are some. So what are the advantages and limitations? So again, marker models are hidden marker models have proved effective in number of domains. The basic theory of HMMs is very elegant and easy to understand. This makes it easier to analyze and implement with the help of MATLAB. Limitations of marker models are the data of marker property. Okay, so give me a second. So I'm sharing my screen to have some MATLAB simulations. So last class we saw everything about uh, power spectral density and all, but we couldn't see how it reflects in practice. So today I'm going to have some demonstrations using MATLAB and also some signal processing basics because in this lecture, in this week 7, sir covered the analog to digital conversion. So I think that is very important for our understanding. So meanwhile, you can tell me like how your go is going on, like how many of you are giving exams? Okay, so all of you are giving exam. That's great. So after marker model, the second topic was analog to digital conversion. So now, like, I would like to explain you through this, the task. So now you have like previously we saw how to generate a signal and that's very fine. But now after generating signal, all the physically occurring signals are analog in nature. All of you agree? Now, first you need to choose a sample times. In order to convert the analog signal to digital, first we need to choose a sample times. So the signal should be generated. Okay. So you can choose a sample time by specifying sample rate, start time, or end time. So we know that in MATLAB, if we have some start end in the between, we have something like interval. So that interval we can separate it using colon. Okay. Okay. So you can see here, like from A to B with interval of 1 by fs, we can generate various things. Okay, we can generate various things. So specify the sample rate. Suppose we have 100 hertz sample rate. Okay, and then a variable name fs. Then create a signal name t that extends from 0 to 3 with the time steps of 1 by fs. So how can we have? So fs is equals to 100. Okay. Then t is the time or the signal 0 to 1 by fs because fs is in frequency domain and you all are talking about in time steps. So 3, 1 by fs. So let's submit it. So you can see the signal, okay, with the frequency steps of 1 by fs. Now, a straightforward way to make a sine wave is to use the sine function, where f is the frequency and t is the time period. So sine 2 pi ft, okay, sine 2 pi ft. Now, the simple thing is, how can you do that? So simple, create a plot of versus t. So suppose let's create sig equals to sine 2 into pi into, again, what is F? So frequency is phi. So phi here it is given, and T timestamps we have already generated with the interval of 1 by Fs. Now plot sig T X and Y, right? So that's great, right? Next is to create a signal with multiple tones, you can add the various sine waves. Can you please answer this for the task 3? I'm waiting in the chat box. Simple, right? So yeah, most of you answered it. So it is, we need to add it, okay? So signal addition is very simple in the signal processing concept, and it's very, very simple in MATLAB. So to create a signal with multiple tones, you can add a sine wave together. So because why multiple tones? Single tone means is a signal of single frequency. And if we are adding different frequency to it, so it is a signal of different frequency, more frequency. So let's add another. So sig is equals to sine 2 pi, here f is 3. Then again t is same, plus again sine 2 pi. Okay, now let's create a plot again. Plot t sig. That's great. So you can see here the single tone frequency, how it looks like, and how the multiple tone frequency looks like. That's great, right? So now try using power spectral function to view the spectrum of this. So let us have this power spectrum, okay? So we know that power spectral is a Fourier transform of autocorrelation function. What was the autocorrelation function? Autocorrelation function was nothing but in time domain, okay, E of xt multiplication of xt plus phi tau, okay. The difference was tau. Now this is in frequency domain. That's why we are doing it in with respect to frequency. Let's run this. Oh, so we have frequency of the power spectrum. So we have frequency of 854 megahertz, and power spectrum is a dB, and this is the frequency. So you might wondering like this, why this is like this. So first of all, let's type help power spectrum. Okay. So power spectrum is to analyze the signal in frequency and time frequency. Okay, so let's first read this. So it analyzes frequency signals in the frequency and time frequency domains, where P is equals to PS spectrum. Returns the power spectrum of X. Simple. Okay. X can be a vector, a matrix, or a timetable containing a double or single precision data. Where when X is a timetable, it must contain increasing and a finite times values. Okay. Now, this P is equals to PS spectrum, like what we use, is a specifies a frequency. Fs is a positive mnemic scalar corresponding to a sample rate of X in the unit of Hertz. Okay. This parameter provides time information to the input and only applies when X is a vector or matrix. Okay. That's why we had this. So using help you can have, and great how good looks like. So I just want to see how many students. Okay, so I hope you all are enjoying and understanding. Also, if you have any doubt, you can stop me anywhere and we can have discussions. Now, this activity reviews the core concept from signal processing. Okay, so what is the background? So let's have some background. You can refer to spectral analysis model or filtering model. So let's have this filtering spectral analysis because I think that is very important for us, and filtering also. Okay, spectral analysis and filtering model are the modules in this course only. So not a problem. So this course, okay, this course uses a clip from the back Valley recording from the Monterey Bay Aquarium Research Institute. You can use the sound in this lesson here. Sound used in the lesson. You can also import the audio files into MATLAB. The signal data and the sample data stored in the separate files. So here, from here, we can see the sounds also. Okay. So this is nothing but a simple sound, okay? I don't know whether it is sharing or not. But so yeah, for your understanding only, I just shared that it's just a simple sound, okay? Now you can import the audio files into the MATLAB. That using audio read, we can import. The signal data and the sample data are stored in the separate variables, okay? So if an audio file comes to the signal and the sample data will be stored in different file. So let's have Vele is equals to audio read. Okay, that's cool. So again, now we have to store that. Uh, MATLAB is actually fun. Okay, I think this is clear to you. So I want you people to first complete these three first task. So plot, how will it look? Plot, really. Plot, really. So that's great. How will it look like? It's in time domain. Now, to view the frequency component, okay, so simple thing, we have to do power spectral. To view the frequency kind of signal, you can calculate the power spectrum with the power spectrum function. And if you don't use any output algorithm, it will create uh, the plot. And let's have, so here my signal name is Pele. Oh, that's great. So you can see the power spectral density. So you can also create a spectrogram with the power spectrum function. So actually I have some bandwidth issues, so that's why switching to some other network. Let's try. So you can also create a spectrogram with a power spectral function by including input spectrogram. So let's create the spectrogram. I hope the internet connectivity is good. So if you are not able to see anything, please say me. So we have signal named as Vele, FS. Now, please write in the chat box, like what is the difference between spectrogram and the power spectral density, with what particular we are having from the observation. So you can see the screen actually. Spectrogram is actually using a short time Fourier transform. So you can see with different time, we are having a Fourier transform. Okay. The frequency is this one, short time. And this is the power level it is showing. So it returns the short time Fourier transform. Okay. With the power spectral density in terms of short time Fourier transform also. So that is spectrogram. Sometimes we often get confused. So like this, you can have a confusion clear. Okay. You can use a low pass filter with the low pass function. Okay. If you don't use any output algorithm, low pass creates a plot. Okay. So let's have low pass. So by default, it is creating a plot, okay? If you don't use any output argument. It's a predefined function using what function? Function name output is equals to input function name and then input parameters for there that we saw it in the first class. Okay, so low pass wave, and you want the filter to be at 0.3. So let's have pass, specify the sample rate as well. So mm, fs was my sample rate. Let me see fs. Okay, so pass at 0.3. I think. Let's see. That's cool. You can see here what was the original signal, what is a filter signal. So again, filter signal doesn't mean that it will go through frequency. So again, you will have these things, and you all are seeing in this in frequency domain. Okay, this is in frequency domain, and this is in time domain. What is the difference between frequency domain and time domain? Time domain signals are in time with respect to time, and with Fourier transform, it converts to frequency domain signal. Okay, great. So with power spectrum and the filtering functions like low pass, you can use the output arguments to save the results to a variable. Then you can perform the further processing also. Repeat the task and again well fit. Because we need to store the signal also, right? Somewhere we need to store. So goes to that's great. Let's go to next class. So you can listen to the original signal with this one. Okay. It scales, but the sound SC command scales the signal before playing it, as opposed to sound command, which doesn't. So then wait till the first signal has finished playing before listening to this, the filtered signal. It scales actually. So I don't know whether you are able to share some. So this was the sound. Okay, let's again play it once again. So okay, let's stop it. So review some signal processing basics. So this audio read was the input um, audio, which was having some audio read file name. Power spectral was some power spectral density. This frequency. Save the power spectrum at this frequency. Display the spectrogram with our input argument as spectrogram. Low pass display the filter signal. Save the filter signal. Okay, we saw this. Visualization was time domain was this much. This was the original blue color. Filtered is this red color. Frequency domain we can see as a blue color. And time domain also we have this things. This is a spectrogram. That's great. Let's go next. So we have something to do with the course. Okay. So you have probably seen some digital watermarks on images like this we can see. But did you know that you can also watermark audio files? That's great. Watermarks can be used to identify and verify the owner of the image, video, and signal data. Sometimes watermarks are very noticeable. Okay, this makes that the owner obvious, but it can be distracting for the media. And if you are a photographer, you might not want the watermark to cover the entire image. Okay, to preserve the media, you could also use a subtitle sub-letter watermark. Okay. An effective audio watermark could be frequency content that you can't hear, but you can see from the spectrum. Okay. So again, watermark for the audio file can be other frequency content that you can't hear, but we can see from the spectrum. For, here are four examples which you will create in this module. Okay. So single tone watermark. Okay. With one single frequency, we are having one watermark. These are the chirp watermarks. For some sort of frequency, we'll have the watermarks. Okay, you're chirping it. Okay. Now again, chirp watermark with interpolated signal. You are chirping it with simply flat. There are some audio watermarks, like we are having some set of frequency where we are doing some watermarks. Okay. The signal that you will watermark in this module is the recording of the flute playing one note. Okay. You try to read this. I'll just have a water. Now, before you watermark the signal, you can visualize the signal in this activity. Let's, okay. So recall that you can import the audio files with the audio read using the separate variables for the signal data and the sample rate. Again, we can see that. Okay. So let's have that signal because the signal name is flute and FS is equals to audio read. The file name is noisy. Okay, tab. And again, that's it. Right. Okay, that's great. A strip plot is a wrap around plot that is very convenient for the viewing entire duration of a signal. Okay, the strips. So uh, let's see, plot the flute for signal in 2 seconds. So let's, where n is a number of seconds per strip and f is a simple time. So let's strips flute to fs. You're just having the plot of the flute in 2 seconds. So here you can see that. Okay. For 2 seconds, 0.51 and 2. So you're having some different signals frequencies. Today, the end of the signal has very large amplitude sound. It makes it difficult to see the rest of the signal. You can extract the portion of signal using array indexing. So from where it is having that? So 1.5 or something like that. So where n and m are the starting and ending indices, okay? To get the first k sounds of the audio, you can use a sample rate to calculate the ending of the index. Okay, to get the first k sounds or seconds of the audio, you can use a sample rate to calculate the ending index. Okay. Now, flute is equals to flute because all are array, right? 1, 2, how much we want? 7. Again, that is multiplied with fs. Okay, I think add the code above strips command so that the plot updates. Okay. So you can see here, you have successfully modified the signal. Okay. Plot a spectrum using PS spectrum. So steps, task. Mm, P spectrum. P spectrum. And that is what? Float fs. You can see here that is nothing but a simple power spectrum density. Okay. In the spectrum, you can see there is a tone around 0.520. Okay, there's a tone. Okay. Now there are other spikes are harmonics or the multiples of 520. Okay. Harmonics are a multiple of 520. For example, the second spike is around 1.040 kilohertz. Oh, 1 point. So here. So here, this again the spikes are going on here with a frequency of 520 hertz. Listen to the sounds before moving to the next session. So we can have lessons also. Sharing the sound. Okay. So by that time, we can see some. So after this, we will see some markup things also. Okay, you can create an audio watermark using a variety of methods. In this lesson, you will bring by exploring the different things to consider when generating a digital signals. Okay, like our thing was like how to convert the analog to digital signals. Okay, you're probably already familiar with the sine wave parameters, but you can use the script to visualize how different parameter affects the type changes. Okay, affect the sine wave. Try changing the amplitude, frequency, and phase. If you want to see the code used to create this plot, you can view here, and output at the right side. Okay, these are some codes. Output and line using this icons. Okay. Now let's see. This is a sine wave. Now if I change some amplitude, okay, okay, amplitude is just changing. Hmm? The amplitude is changing. These are the physically occurring signals that is analog in nature. Is frequency changing? No. Let's change some frequency. Okay. Let's change some phi. So I think I can't see the phi changes. But yeah. So phi has been changed from 180 degrees. Phi is nothing but the orientation. Okay. Okay. Now sampling theorem is the main thing to convert analog to digital signal. So let's see this one. Strange.
Most real-world signals are continuous functions of time. You can get
So most real world function are the continuous in time.
the value of the signal at any time you want. But to efficiently process signals on most computers, you need a discrete time signal.
So what is the need for discrete time signal to efficiently process a signal on the computer? Are you getting this point? Efficiently process in the sense that that should be binary. Okay?
This means you only have data at specified times. To sample a continuous time signal, you need to choose a sample rate based on the frequencies that you expect. Different applications encounter different frequencies that you expect. Different applications encounter different ranges of frequencies. Seismic activity is relatively slow. Most earthquakes will generate waves below 10 Hz. Compare that to audio signals. A human ear can hear sounds up to 20 kilohertz. If you tried using the same sample rate for both applications, a rate that's reasonable for the audio signal would end up storing way too many samples of the seismic signal, resulting in higher computer memory usage and
So again, you have different type of applications. So for that, we need to have different type of data samples. So is for some applications, you will require some more applications, more data to be stored. Like if you can have seismic waves. So for that, some samples are fine. But for the audio waves, more samples are required because we can hear up to 20 kilohertz.
a slower computation time. On the other hand, what's reasonable for the seismic signal won't be enough samples to detect the frequency in the audio signal. So, how many samples are enough? Intuitively, you need to sample faster if your signal has higher frequencies, because your signal is changing faster. For a real audio signal,
So what is this saying that if you are sampling the signal faster, then you will having the higher frequency. Okay, try to understand this. What is sampling? Sampling is nothing but a switch. Taking one sample, one, two, three. Again, if the switch is working very fast, one, two, three, four, five, six, seven, eight, nine, 10, like that. So you'll have higher frequency range.
so how many samples are enough?
So again, question is how many samples are enough?
Intuitively, you need to sample faster if your signal has higher frequencies, because your signal is changing faster. For a real continuous time signal, the spectrum has content at your signal's frequency and the negative of that frequency. To get a discrete time signal, you need to sample the continuous time signal at a regular interval, determined by your sample rate. Once you have enough samples, you can use FFT to estimate the spectrum. The resulting discrete time signal has replicas spaced by your sample rate, and there are infinite positive and negative replicas. Well, this is a pretty simple signal. It has just one tone, so it's easy to distinguish between the original spectrum and the replicas. Most real-world signals aren't just one tone. There's frequency content up to some maximum frequency. In the discrete time spectrum, all these frequencies are replicated. Remember that the replicas are spaced by your sample rate. To keep your original frequency content untouched, your sample rate needs to be greater than twice the highest frequency.
So again, in practice, in real world, we don't have a single tone frequency existing, right? So we can have various type of frequency existing signals, like square wave, triangle wave, like here we can see. But when we convert to time frequency domain, in that case, the signals may collapse to each other. And in that case, you can have an information loss. So that's why the sampling should be done such a way that it should not have the max fs should not be greater than equals to 2 f max. Then in that case you will have the collapsing. So for that we need fs greater than equals to 2 f max. In that case there will be no uh, loss at the Fourier transform.
In your signal. This is sometimes called the Nyquist rate. If
And
you
that
use
2 fs is called Nyquist rate.
a sample rate that's smaller than the Nyquist rate, the replicas start to overlap. You might expect only the higher frequencies in your data to disappear. But when this information is lost, you have interfering power at lower frequencies too, called aliasing. Aliasing occurs when a signal is sampled in a way that makes it indistinguishable from another signal. Remember that your goal is
Aliasing in the sense happens when the fs is less than 2 fm and the signals are collapsing to each other and you can't differentiate between two signals.
to accurately represent a continuous time signal with discrete points. In order to get your original signal back, just remember to choose a sample rate that's greater than twice your highest frequency.
Okay, so we have analog and digital signals. Signals in the real world are analog, as I was telling. But in computing, most signals are digital or discrete time. How does this affect your signal processing? So signal, continuous time, this is a frequency. So discrete time, as you can saw in the video, so signals in real time are analog or continuous, but in computing this how? So for real valued signals, the magnitude spectrum is symmetric around 0 Hz. Okay, this is the real valued spectrum. As you saw in the video, you introduce the repetitions in the frequency domain when you sample the signal in the time domain. The repetitions are repeated every fs. Okay, you can see here at every fs. This is the repetition here, and it is repeated every fs. In general, you want to keep the frequency at the same location in analog and digital signals. To do this, you choose a safe sample rate so that repetitions don't overlap with the spectrum, and the sample rate should be at least 2 FM max. So again, this scripts generate a sine wave with a single tone at f hertz. Okay. In this activity, you will modify the frequency value and the sample rate to see the effects of aliasing. Okay. We will see the effects of aliasing here. In the time domain plot, so time, this is a time domain plot. Okay. The blue line shows a smooth curved sine wave. This might be how are you accustomed to seeing the sine waves. Discrete time signals, the time domain can look strange. Oh, okay. In the plot, the red points are the sample points. Which are the red points? Okay, these two are the red points. That is the sample points. And the black line connecting them. So discrete time. Okay, you may not recognize the sample points as the sine waves, but if you sample fast enough, the frequency domain plot will show the correct frequency. Modify the slider value so that the sample rate fs is greater than 2 µs. So here you can see if fs is greater than 2 fm, you can see at least that you are having these points greater. Again, I'm sampling more and more. So yeah, I'm sampling more and more, then it is showing like this. The frequency domain plot is below the time domain plot. Notice the frequency content is correctly placed at the f value. Yeah. So this is a frequency domain plot. So here it is correctly kept as a f value. Okay. Modify the slider value fs is below the Nyquist rate. F value is 0.7. And here you can see. In the video, you saw the spectrum of a discrete time signal repeats every fs when fs is greater than 2 fm max, like in this plot. Okay, it is positive or negative frequency it is showing. So 2, then 1, 2, 3, 4, 5. Blue line is again repeating after this. So the vertical line at fs by 2, that is 2.5. Okay, it's called the Nyquist frequency. It's called the Nyquist frequency. Marks the x limit for that you will see from the this plot shown above. So fs by 2. Okay, fs is equals to should be greater than or equals to f max. And fs by 2 is the Nyquist frequency it is showing. In this plot, fs is less than 2f max. So there is a aliasing. The alias tone at 1 hertz is a repetition tone at -2. 1, 1, 2, 3, 4, 5. You can see here. Okay. So in the frequency domain plot, notice that the frequency content isn't located at the slider value for f. Okay. Recreate the example from the second slide of the background by setting the frequency slider to 2 and sample rate to 3. 25. Again, it is. As you saw in the slideshow, the light stone is located at 1 hertz. Okay, because fs should be 4, but it is at 3. So 4 minus 3. Try a different combination of frequencies and sample rates. If you want to use a code, you can see here. Okay, time vector n is equals to 5. Okay, you have 0, 1, 2, 3, 4, like that sample index. When you import a signal into a MATLAB with audio read, you get the signal and the sample rate. You can label each point with its sample index. In MATLAB, array indexing starts at 1, as we know. In the signal processing, sample index starts at 0 because it corresponds to first sample at 0 second. The first sample index is 0 and you need n indices. So this last index is n minus 1. In this example, there are 5 samples, so sample index from 0 to 4. Okay. So here n is equals to 5 and the sample index, okay? Fs is equals to 2. So how will you sample it? N by Fs. Why n by Fs? Again, this is 1 by 2. 1 by 2, 1, 3 by 2, 2. It is sampled at a frequency of 2 hertz. If you want time vector in units of seconds, you can divide the sample indices by your sample rate. The spacing between each point is 1 by Fs. Here the sample rate is 2 hertz. So the frequency between each sample is 1 by 2. Okay. In this activity, you will generate a simple watermark for the fluid recording. You'll add the watermark signal with the audio signal. So the signals need to have the same length. To ensure both the signals have same length, you can create a vector. Okay. You can create a time vector. So for the flute recording, start by creating this one. Okay, where n is the length of the signal, you can use the name number function to find the number of elements. So if I see n is equals to number, so this is the power spectral density. Okay, colon operator creates an equally spaced row vector. The signals are conventionally stored in MATLAB as column vectors, so you can use the transpose result. Okay, fine. Calculate the column vector that contains a sample index of each element in flute. Store the result in T. 0 to n minus. I think great. So to convert from the sample index to the time value in the seconds, you can use T by Fs. Convert T is equals to N T by Fs. So Fs might have been described here. Okay. Okay. The power above 5 kilohertz is around minus 90 dB. 5 kilohertz minus 90 dB, we can see, which means the frequency content is not audible. Any location above 5 hertz would work for the watermark. So you can try inserting single tone at 6000 kilohertz, means 6 kilohertz. Generate a tone. So single tone we can create using sine. So Wm is equals to sine mm, by yeah, then plot. I don't know whether it is correct or not, but yeah, let's see solution. Okay, so if we want to see something, so power spectrum only we have to do. So I have done almost everything. P spectrum. So again, there's a single tone frequency at 6 hertz, 6,000 kilo, 6,000 hertz. Now you can combine the audio and the watermarks. So add the audio, name the result mark, and plot the spectrum. So whenever the plot spectrum is asked, so power spectrum is asked, okay? So after is equals to Wm plus flute P. So correct. So we can see here, these are the after 6 kilohertz, we can actually do the low pass filter, or this is showing the watermark here that we added in the audio file. Now you can clearly see the watermark at 6 kilohertz, but it is also overpass the flute spectrum. Ideally, the watermark would be identifiable in the spectrum without altering the quality of the audio. So play marked with the sounds XX, and the watermark is much louder than the flute. Try scaling the watermark so that it is audible, but tone is still visible in the spectrum. So we can, for example, you can do like this. So again, sound SC. Just so you are actually doing the reducing the amplitude of this WM. I don't know what is showing something. Let's only have this. Okay, so previous thing came. So I hope you're getting some things and trying to understand what we are trying to do. So the audio spectrum has lot of frequency spikes as we can see here. You want watermark to be easily recognizable in the spectrum, but a single tone can be difficult to differentiate from the harmonics. Instead, you can try having some another common signal which is known as chirp signal. Okay, the chirp, the frequency at time 0 is F0. The frequency at time T1 is F1. So T F0, T1 F2, chirp. So create a chirp signal WM using the vector type T. So this is a time, number of flutes, and this is a time in seconds. So WM 06,000 Again, I didn't provided this FS search. Let's see the solution. Where I have done mistake? Nowhere. T. Okay, it is starting at T. Oh, so sorry. Not like this. Instead of spike, the chirp creates a block of power in the spectrum. So you can see here, it is showing a block of power. This is because chirp sweeps across the frequency from F0 to F1. Try listening to WM, okay, using sound X. Plot the spectrogram of the chirp using power spectrum. So this is the spectrogram. Combine a watermark and the audio. Name the mark and then plot the spectrum. I think the signal name is flute only. Okay. So we can view the spectrogram, the watermark also. Then we can some scale or we can see something. So now the statement comes that upsample and downsample. So far, you have chosen a sample rate before generating your signal. But if you are working with the existing signal data, your signal has already been sampled. Okay. When you need to change the sample rate, there are multiple ways to resample a signal to a higher or lower rate. So upsampling, downsampling rate are the simplest methods. Okay. So when we are generating a signal where t is equals to nts, okay, but at the same time, any doubts? Okay. So when we were generating the signal, we had already had a sample rate. So how to do upsample and downsample? Because we want some signals to be used so far. Upsample, downsample. Here's a stem plot of a signal. Up. Okay. So here's a stem plot of signal. Upsample will looks like upsample operations add zeros. The signal was upsampled by a factor of 2, so a 0 was added between the sample. So 1 0 had added. Okay, you can see these were the samples. So 1 0 added in every samples, but means n minus 1 zeros. Now let's see downsample. So you're having these samples. The downsample operations removes the samples. The signal was downsampled by factor 2. So every other sample was removed. So here this was removed. That's great.
When you sample a continuous time signal, you can try out different sample rates. But if you need to change the sample rate of a signal that's already sampled, you could get unwanted frequency content. For instance, sometimes you're stuck with two devices that have different sample rates. Maybe your microphone records at 8 kilohertz, but your audio equipment has filters designed at 48 kilohertz. If you want to use the 48 kilohertz device, you need to change the sample rate of your recording first. You might be tempted just to insert zeros into the 8 kilohertz signal. This is called upsampling. When you add zeros to your 8 kilohertz recording, you will see high frequency content appear. These copies of your tones are called signal. This is called upsampling. When you add zeros to your 8 kilohertz recording, you will see high frequency content appear. These copies of your tones are called images. Because your recording was sampled at 8 kilohertz, you know that you don't want these in the upsampled signal. To remove them, you can low-pass filter your upsampled signals. You know that you don't want these in the upsampled signal. To remove them, you can low-pass filter your upsampled signal. The combination of upsampling then low-pass filtering is called interpolating.
So again, when we are adding some upsampling, so the zeros are added in the time domain. Okay, n minus 1 zeros are added in the time domain. But as we just now say that with the zeros adding in the time domain, we will have the copies of the same frequency signals in the frequency domain. So, but we don't want that. Okay, so that again, it will be for the upsampling is followed by a low pass filter. So the whole process is called interpolation or interpolating.
On the other hand, when you want to decrease your sample rate, you're downsampling. In this case, you risk violating the sampling theorem and introducing aliased tones. To avoid this, decimating will low-pass filter before downsampling to remove frequency content above the new Nyquist frequency, greatly reducing the aliasing.
But at the other hand, if you are downsampling, the low pass filter will be added at the front before downsampler, because in that way it is reducing the frequency components which are greater than Nyquist rates.
Now, interpolating and decimating require integer factors. So, how do you change the sample rate by a non-integer factor? Well, you interpolate first and decimate second. Then the two low-pass filters can be combined. The resample function in MATLAB can interpolate, decimate, or both with a single function call.
So you can see here, um, we want only functions to integer values to upsample and downsample, but the the upsample is followed by a low pass filter, and uh, 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 then downsample is free followed by a low pass filter. And if we combine four of them together, then in that case, that will be a resample module in the MATLAB.
In the next activity, you'll listen to a resampled signal with and without the low-pass filter and explore the effects on the resulting signal.
In this activity, you'll start with a signal that is properly sampled. The sample rate is above 2 max, 2 FM max. There are two tones, one at 300 Hertz, another at 3000 Hertz. So 300 Hertz and 3000 Hertz, two tone frequency. Then you will downsample the signal by a factor of 6, which will introduce aliasing. Aliasing in the sense, you know, 3000 multiplication with 3000 divided by 2 was Nyquist frequency. Okay, you can see what happens here in the spectrum. You can listen to the signal to hear the effects. Here the tone at 300 Hertz is less than the frequency, Nyquist frequency, so it's still in the correct location after downsampling itself. But the tone at 300 Hertz is above fs by 2, so it will not appear in the plot. Oh. So instead, you will see an alias tone at 1000 Hertz. This is the 1000 Hertz that is coming from the above other signal itself. So instead, you'll see an alias tone. The alias tone is repetition of the tone at minus 3000 Hertz. Minus 3000 Hertz plus fs is equals to 1000 Hertz. Okay. To downsample a signal, so that there is no aliasing, you can use a downsample function where n is an integer downsample. So name the result sick, bad is equals to downsample, sick, what it is. Downsample, sick, signal name is sick only. Okay. Plot the spectrum, the PS sig bad FS by 6. So yeah, you have this spectra, okay, downsample. Previously you had this. So downsample shows there are some frequency components that will be having more than fs by 2. The tone at 300 hertz is at the correct location, but as you can see in slideshow, the tone at 3 kilohertz is now aliased to 1 kilohertz. Okay, okay. So reduce the aliasing, you can use an anti-aliasing filter before downsampling. The resample function will include this filter for you. But to see how it works first, you can try making your own. Y is equals to low pass fs mu by 2. You can try making your own. Low pass x fs mu by 2 fs. Okay. Z is equals to downsample yn. If fs mu by 2 is a Nyquist frequency after downsampling. Okay. And what was the previous sample? Okay. The low pass filter sig, the pass band frequency should be where this frequency, Nyquist frequency will be located after downsampling, then there is a sig filter. So let's have sig filter is nothing but fs by 12, right? Because it is fs by 2 new frequency divided by 12 is fs by 12. 12. Now pass band. So let's have mm, the pass band frequency where low pass filter was sig. So let's have low pass filter y is equals to low pass sig sig fill fs. Then now after low pass, let's plot this, repeat this. So I think we have some solution. We ran into some problem. Let's see some solution. So sig field. Oh, okay. So sorry, I understood it wrong. Why 2000? Because the fs was how much? Fs by 12. Okay, fine, fine, fine. I misunderstood this. Yeah. But in MATLAB, sig field exists. Sig field correctly defined. I think yes. What is the problem now? Sample. Oh, fs by 6. No? Oh, so sorry. This is sig field. This is So this type of mistake we often do, but not a problem. Okay, so now it is correct. So we can see here. Uh, Again, the aliasing is there. The power spec of the alias tone decrease by about 10 dB. Okay. Now you can try using the resample function to decimate the signal. If P and Q are the integers resample factors, the output Y has P by Q samples from X. Okay, when you decimate, P is 1 and the output will have 1 by Q samples. So decimate the signal sig good is equals to decimate resample. The low pass is already included in this. Sig by factor 6. So, but this time you use a resample function. So 1 and I think 6. Let's see. Again, where I'm doing mistake, I sure. Sig good resample 1 6. So sorry. The sampling will happen 1 6, right? Sig good FS by 6. Spectrum is asked. So we have seen enough MATLAB codes where we are converting in analog to digital converter. We saw also hidden Markov model. Markov model, what are the basic things like what Markov model does. We also saw the correlation and the convolution, which was covered in week 7. I think we can go through the questions. Yes, time is already going to be up. So first is we can use MATLAB to perform the time frequency analysis of the signal. The answer is true. You can use the MATLAB to perform time frequency analysis of the signals, where MATLAB provides the various tools, function toolboxes for signal processing, as we have already seen. Short-term Fourier transform, continuous wavelet transform. We will see all these tools in subsequent module. The command IR gives the eigenvalues as stored in the order of ascending. Okay. uh, it will start from 0 to n. It is actually giving the vector. The command I gives it a similar computation involves typically computes the eigenvalues in the matrix R. Okay. The eigenvalues are sorted in a descending order by default, so option is the correct one. Okay, it represents the scalar value associated with the eigenvectors of the matrix R. Okay. The Fourier series maps a signal from basic with an uncountable coordinate to basis with countable coordinating. Okay, that is correct only. Where because in you have the Fourier series. Okay, Fourier series is the way of representation of signal in the time domain in the harmonics of sine and cosine, and it is only defined for the periodic signal. So you have the signal in the periodic. Periodic is actually it is showing many up to many infinite time series. Okay, now it actually maps with an uncountable. Uh, so let's break it down. Countable, uncountable. Sure. A continuous time signal such as xt exists in a function space with an uncountably infinite number of basis functions. This is because for each time point in t, the signal can take any real value leading to an uncountable set of possibilities. The countable basis is the Fourier series represent the continuous time signals as sum of sinusoid functions that are periodic in nature. And these sinuses are formed on a counted basis because they are indexed in the integers sine 1t, sine 2t, cosine 1t, cosine 2t. Okay, the coefficients of these sinuses determine the contribution of each frequency component of the signal. Okay, so the Fourier series accomplishes the mapping of a signal from a uncountable basis to a countable basis, that is the sum of sinusoids. Okay. Two complex valued signal xt and yt are called orthogonal when their inner product is zero. So inner product in time domain is nothing but x transpose y is equals to zero. Okay, where you are summing it. What is the inner product showing? It is a correlation. What is correlation? Correlation is showing the similarity between two signals. Okay, what is the similarity? So if you are multiplying each component of two signals, suppose two signals are there. And if you are multiplying this particular component, this particular component, this particular component, this particular component, and finally you are summing it up, and the sum is tends to zero. So then they are both are orthogonal to each other. Like they are both orthogonal to each other. So in that case, it is orthogonal. So the first option will be correct. Okay. No, not is the first option. Second option will be correct. So answer is. So it is not written properly. XTYT. The correct condition for the two is so okay. So again, inner product for the real complex valued signal is conjugate. So I couldn't understand. This is a conjugate. So the first option is correct. Okay. The Fourier series maps one period of a discrete periodic signal to so discrete. Okay. Or continuous discrete. So what should be the answer? Please tell me. So Fourier series. So Fourier series, as we have seen, what is Fourier series? It is showing a real valued signal in time domain, and that is a periodic. It maps to the discrete frequency components. Why? Because you have a by 2 plus ak cos 2 pi k f naught t plus b by 2 sin 2 pi k f naught t, whereas cos 1 is the even signal part and sin 1 is the odd signal part. Okay. Given the variance of a random process and its innovation components, then the maximum processing gain of by LPC is again it's a this one that is clearly explained in the class also. The, the processing gain is this one linear predictive coding. Okay. So yeah. Given a signal sampled at W samples per second and is quantized in L level quantizer, the resulting signal 8 is nothing but W log 2 L. Okay, why log 2 L? Because L level quantizer. So it is multiplied with the L log 2, where you have number of bits is V max minus V min divided 2 power n, where n is log 2 number of levels. 2 power n is number of levels. Okay, where n is equals to log 2 L. Suppose L is equals to 2 power n, where n is equals to log 2 n, where it is sampled at W. So W into log 2 L. Okay, so answer is 1. Sampling rate and quantization level. Okay. So please, thank you so much for joining my class. And uh, I'm really very honored to help you all. So I think Ramesh is there, Raja is there, Manisha is there, Dishant is there. So 5 students joined my class today. So please try to continue in the next upcoming class. Okay. So goodbye.